Statistics is the science of reading the data. These days, we are in the age of data and information. You need to be able to know how to handle the data, how to look at it, and how to analyze it. To be able to come out with a conclusion about that data. Is it a good data? What does it tell me, regardless of the engineering field that I'm working in or I'm focusing on? Now, the objectives here would be to analyze wide variety of data sets. We will try to apply the appropriate technique in various data analysis situations, and we will try to create graphical representation of the data points using graphs and histograms. Now, I always say to my friends and to my students, the best sciences come from the least expected places and or people. You are sometimes in a place where you think, well, I'm just having fun here. I don't think I will learn anything today from this place. But you ended up coming out with a conclusion that you wouldn't get it anywhere else. Here we have John Nash. For those of you who are a movie worm, if you will, there's the movie called Beautiful Mind. This movie is representing the life cycle, or let's say the life story of the scientist John Nash. The actual picture of the scientist John Nash is over here, and this is, I don't know what's his name, Russell, who's representing him in Beautiful Mind. The thing is, John Nash was focused and interested in mathematics and statistics. So one day they went to the bar with his friends and they're having fun. Then one of his friends told him, if you go to that girl and pick her up over me, then you win. Otherwise, I would win. And from that moment, without going into details, he discovered a nice statistical-based science called the game theory, which means if two people are competing against the same thing, that thing value will increase. But if nobody compete against that thing, then that thing value will decrease and will be obsolete or not important at all. So that was the basic concepts of the game theory that John Nash got the Nobel Prize on that work. Now, statistics is defined as a branch of mathematics. Engineers use statistics in decision making, and engineering applications always generate thousands of data sets that you want to use to be able to draw conclusion about that topic. Now, the more advanced you will be in reading and analyzing the data, the more successful you would be. I would say personally, not only in engineering, but in many engineering fields or in your company. Either you own that company, or even if you are just working with that company. Now, the first topic that we're going to talk about that's related to statistics is called frequency distribution. Now, large data is considered as a treasure of information, but that kind of data means nothing until you're able to read what does that data mean. Now, frequency distribution, it's defined by the textbook as a systematic collection of data that is illustrating the number of times a given value or collection of values occur. Right down here, a group of numbers, 1, 2, 3, 4, 5, 3, 2, 5, 3, 2, 5. Now you look at this data set. For frequency distribution, when you look at this data set, you are trying to see how many times does each number get repeated. So if we make a line under each number, or we can go, it's going from 1 to 5, if you will. So 1, 2, 3, 4, 5. I would say that's the number, and that's the frequency. Now, number 1, how many times it got repeated? That's once. Number 2, 1, 2, 3. Number 3, 1, 2, 3. number 4 once, number 5, 1, 2, 3. Assume there's another 5 here just for the sake of the example. So how many times the 5? 1, 2, 3, 4. Now what we did here is considered as a frequency distribution. How many times did a single value or a single data set or a single number, this number could be the pressure of a vessel, it could be the speed of a car, it could be the atmospheric pressure on a certain planet. So here you did your frequency distribution analysis, and based on simple basic comparison, you know that number 5 is the highest frequency number. So that's the frequency distribution analysis in its simplest form possible. So now we have an example. The example is saying the percentage of body fat in 45 men under the age of 50 is listed in the table right here. Now, the second table is a way to arrange the data that you can decide what's the frequency distribution of the body fat for those 45 men. Now, there's something you need to know. Here we did value and frequency, as that's the simplest form possible for frequency distribution. While here, you can see, so this is the data. This is the data we got. Those are the values of body fat for 45 men. So we have 45 same sample data sets. What we did here, we made a range for ages. So we said, we made a range for the values of the body fat. We said if the body fat percentage 40 to 89, then that's one group. Then 90 to 139, another group. 140 to 189, another group. All the way to 390 to 430, if I'm reading right. Then that's this way, because you have too many data, then you do the range of each data specification, and you start to count here. This is the frequency, or let's say the count. How many times did we see values within this range, and how many times we see values in this range? Then we type down our frequency as needed. The thing is, the only tricky part here is the range. I can decide a range different than the range you decide. But for the sake of a problem, if we have a problem that we want to solve, for sure we will make it specific for you that to have the range or the types incremented in a certain way. Now you got your range versus frequency. Now you want to draw it in a visual way to be able to see it, as we said before, as an image and be able to analyze it. This kind of graph, that's the bar style graph. Some people in statistics, they call it as a histogram. So histogram is the bar representation for your data. So what you can see here, body fat percentage on the x-axis, and the frequency, or how many times did we have people within that range, on the y-axis. And that would be the histogram. We use it a lot in statistics. Now we have guidelines on how to construct efficiently the frequency distribution. It's recommended to use 6 to 15 classes or types of UL for your data, and select the classes that will accommodate all the data points. As we saw in the body fat percentage, you can't exclude a data set unless you announce that. So you're gonna include everything in your range or in your specifications or sorting, if you will. Now we need to make sure every data point fits only in one class. So you don't want, in your range here, you don't want a certain value that will fit 4 to 8.9. I was seeing that 40 as I'm getting near. So 4 to 8.9, you don't want it to fit here, and the same data point will fit here. That will kind of degrade or lower the accuracy of your data analysis. And we need to try to make the class intervals of equal length. So if you need the ages of people, you say people from 20 to 30, the next range would be 30 to 40 with an increment of 10. You can't go 20 to 30, then 30 to 35. It would be inconsistent. Now, the other type of statistical measures or statistical analysis is called the measures of central tendency. What's central tendency? It's the tendency towards the center as it means. Now, we can define it in your textbook as determining a single number that will describe a unique characteristics about the data. Now, central tendency, under that we have the mean, and we have the median, and we have the mode. Now, the mean, of course, you know the mean, which is as mathematically can be said as the average. That couldn't be accurate all the time, but it's sum of all the data points divided by the number of those data points. Now, there is two types of mean. There is the sample mean, and there is the population mean. Now, there's a certain number, I can't give it to you here, but like if you have a sample, let's say you can have a convention like any sample set under 10 samples, then it would be as a sample mean, while anything greater than 10 would be a population mean. In your textbook, unless I slip it, I know there's something for the variation that we're going to learn moving forward. There's a limit to which time you say sample and when you say population. But for the mean, I didn't see that anywhere. So population mean, whenever you have data points greater than 10, that would be population mean. Don't quote me on that, but like it's just for the sake of explaining. Now, both of them mathematically are the same. Either you go with x bar or you go with mu. We call this as mu. So this one, of course, mathematically, it's the summation from I equals 1 to n of xi. It means like regardless of how many samples you have, you combine them or you add them all together. This is a summation. I believe you are familiar with that. Divided by n, which is the number of those samples. So here, we have those numbers, 5 plus 5 plus 5 plus 6 plus 7 plus 7 plus 14. Let's say we have those data sets, 5, 5, 6, 7, 7, 14. What's your mean in this case? Mean would be the summation of those, right? Like 5, I'm just repeating here, 5 plus 5 plus 5 plus 6 plus 7 plus 7 plus 14. That would be 49. Divided by how many samples we have? 7. So we divided the summation of the samples over the number of the samples, and that would give you 7. Now there is other definitions or measures of central tendency. We have the mean that we define now, then we have the median, and we have the mode. Now the median is, as it says, it's the number in the middle, and the middle here, let's say we have 5, 6, then 7, then 14. It's not like the middle number regardless of the value. It's the middle number of the data set as you are preparing those data in ascending style. So you go 5 all the way to 14. You can see here we have 5, then 6, 7, 14. We have 7 samples, so the fourth one would be the central. So there's 3 samples on the left, 3 samples on the right. So the median in this case would be 6. And the mode represents the number or the data set that appears the most along your data. Like any number that show up more than others, you can imagine it as the frequency or the frequency distribution that we talked about. So here we have number 5 is the number that mostly repeated. And for the range, it's not in your book anyway. Median and mode is not represented or not mentioned in your book, but it's good to let you know. The range, of course, how the data are ranging. What's the lowest value? In this case, 5. And what's the highest value? 14. So my range would be, my range of data is 5 to 14. Now the big elephant in the room, or the important one, measures of variation. Now the word in English, variation, what does it mean for you? So variation is a measure that indicates how much the data are distributed. Another definition for it, how much each number in the sample deviates from the mean value. So variation can be represented as the equation of standard deviation. Sigma is the population standard deviation, n is the size of the population or the number of samples, xi is each value from the population or the samples, and mu is your mean. Now, when you draw the standard deviation, the data graph would look like this. Now, if you take this point represents the mean. Remember when you found the mean, like the average of the data set? The mean would be here. And as far the data point is getting away from the center or the mean, the more it's being deviated from the center. That's why they call it standard deviation, because it shows you how data are deviated away from the mean to the left and to the right. Now again, same as the mean, you have a sample standard deviation and you have the population standard deviation. In sample standard deviation, your book is saying any sample size under 30, like you have a 30 data points or less, then you go with the sample starting with S. But what would change here, it's a little different than the mean. In the mean, same equation here, it's a little different. So you have X bar is still average, but instead of N, you are dividing by N minus 1. So if you have 7 data points, that's going to be divided by 6, not 7. While here, you still divide by 7 as a population. Now, we said you find variation through standard deviation, but if you want an equation for variation, what you're going to do, basically you give, you make to the left-hand side of the equation to the power of 2 and the right-hand side of the equation to the power of 2. So sigma squared means deviation. Sigma is standard deviation, and sigma squared is variation, I'm sorry. That would equal, same thing without the square root, the summation of xi minus mu squared divided by n. There's no standard variation. Standard deviation or variation. Standard deviation is sigma. Variation is sigma squared. In engineering, there is the concept of 3 sigma, 6 sigma quality control. What they do, they are given a kind of deadline or a constraint for their data. So the variation of data, the variation of their devices, let's say if they're making a device, shouldn't be 30% away from the performance of the best device they're making. So it's like a kind of a quality measure for their products. So that's why you hear 3 sigma and 6 sigma concepts. So a Midwestern University campus has 10,540 male students. Now, using a random selection process, 50 of these students were chosen and weighed to the nearest pound. The raw data were recorded in the table we see on the right, table 10.3. The data were then grouped as in 10.4 in ranges and frequency, and the histogram will be shown. Calculate the sample mean, sample standard deviation, and sample variance of the data. So the data in table 10.3, this is the data. They created already for you the range and frequency. You just want to find the mean. You can find the mean. That's the easiest one. But here it's a sample mean. So we got to go back in the slides, make sure sample mean, is it the same or different than the population mean? In this case, it's the same. So just write down your equation for sample mean so that we can move back to the question. Well, if your sample size, if the data set less than 30, you go with a sample standard deviation, that one. S stands for sample standard deviation. Sigma is for population standard deviation. Here's your sample mean. As we said, sample mean, population mean, they are exactly the same. So don't worry so much about it, but in standard deviation, you gotta worry about it. I equals 1 to n, xi divided by small n. So this is the data given to you. Then they make the frequency distribution here. Do you go with those or those? That's right.
That's not.
That's right.
Yes.
Yep, that means nothing in this case. So 164 plus 171 plus 154, blah, 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 all the way to 159. That will give you 8,037. So I have 1, 2, 3, 4, 5, multiplied by how many columns? 10. So that will be an easy 50. Xi, you are annotating which sample point you are talking about. So you could take finding standard deviation for all of them, or take the summation of the xi. Either you take x1, x2, x3, and so on. Here, the summation will distribute after you unlock the squared parentheses here. It will be xi minus 2x bar plus xi squared, I believe, mathematically. Then you plug in the summation into those, right? So xi, you can say, in this case, x1. So it could be now x1. Then I go plug in 164 minus those and so on. Then x2, then x3. Or you take the summation of xi's, which would be in this case what? So the summation of xi squared you see here. So it was 1,296.66. That's the summation squared. So you got to do that here. He already did it for us, but it's important to know what happened, you know? So you have the xi squared minus the xi squared to the power of 1 over 2. That's the square root. Then multiplied on the denominator n by n minus 1. In parentheses, he took 164 minus x bar, so minus 160. So 4 squared 16 plus 171 minus x bar minus 160 squared plus 154 minus. So it's just a lengthy, doesn't make sense process. While here, distribute mathematically the summation, and you'll be good to go. Now, what's the variance for a sample? That's the third. You need the sample variance. Sample variance would be s squared, which equal the summation of xi minus x bar to the power of 2 divided by n minus 1. And that would be 4,793 divided by 49 samples. That would give you 97.8 pound mass squared. And of course, you know the histogram, you just had the ranges that you had in your frequency distribution analysis, and you distribute them in a bar style. You have weight in pound mass versus frequency, and you'll be able to represent the data this way. Another example, safety corridors are established on certain roadways. A driver is expected to turn on the headlight and pay special attention to the posted speed limit in these corridors. In one of these safety corridors in North Mexico, the posted speed limit was 75 miles per hour. Department of Safety made a radar checkpoint, and the actual speed of 36 vehicles that passed the checkpoint are shown in our table to the right. So they're checking the speeds on a traffic light or whatever you think it is. Now, for this data in mind, we need to do hand calculation and use our Excel spreadsheet to solve C, D, and E. And for A and B, we're going to do it by hand. Now, we need to make a frequency distribution table using 5 as a class width. It means there's a 5 increment between each data set. Then we construct a histogram from that frequency distribution. Before we go Excel, I mean, you can go Excel, that's fine. If you want to solve the whole thing in Excel, you can. But if you want to do it by hand first for A and B and do the rest in Excel, we can as well. Now, the table, what would you do with it? How would you do it if you start to solve it? How would you do it? Just put it as it is, like 70, then 78, or what would you do? To make it easier, I mean, there is no right and wrong, but to make it easy, what I would do, I would create like the sample number, then I create the value. So I have them, all these data as one column, so I can handle them, find the mean through equation, finding standard deviation, and so on.
So not rows, columns, just one.
I will, so here I will see what I will do. Let me increase the size. I would say sample number. Like 1, 2, 3, 4, blah, 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 you know? Those mean nothing, just for preparing the stuff. Now here, I would say, you can call it data, you can call it sample value, you can call it anything you want, all right? That's one. Now the data, I start to type in my data, starting with my 70, right? I have 70, then I go 78. Either you go column by column or row by row. Those rows and columns means nothing. He just represents them for you this way. You can make them in one column. That's the right way to do it, unless he specifies something different. Okay, let's go 70, 78, then 70, 86, 76, 75, 69, 80. In this case, histogram is a bar chart. So this looks like a bar chart for me. What else he want? He need to find the sample mean. We go down, all the way down to those data and select where you want to show the sample mean. So maybe I want to show the sample mean here, right? I can call it sample mean. And, you know, always keep the beauty part of your work, you know, as much as you can. I would say sample mean and give it yellow. Why not? You know, it's free. Sample mean. So I will show my sample mean here. How to find sample mean? What's the equation of sample mean? Like the summation over the number, right? Now in Excel, luckily, we can find the summation. So I can here write summation, and I can create an equation for that. Equal, just type in SUM, open parentheses, there's some if and other stuff. There's a function called sum that finds you the sum of these samples. So I can go sum, open parentheses, go from the first value you want all the way down until you're done, which is until 92. I go up in the equation bar, close parentheses. That's the data I want in blue. I hit enter. My summation is 2,716, right? Sample mean equals the summation, right? Divided by how many samples I have? 36, because we gave them a number, right? So I can use this number, that's fine. Or I can just highlight them all, but that's gonna give you a summation. And that's gonna give you sample mean 75.44. Looking logically for what we are solving here, speed, so 74 is making sense, speed, if you will. There is even an easier way to do it. When you're done with this, I will tell you the easy way. Now, easier way, you can either use average. We know that the mean is average, but sometimes it wouldn't be the average. You can say average from here all the way to here. What's the average of those guys? 75.44. I'm not sure. Let's see if we have a mean here. No, you don't have mean. There's a median, but there's no mean. So average. You can use A, you see, AVER, like the word average, open parentheses, select from here to here. That's an easier way. Instead of having two steps, summation, then sample mean, you can have just the average right away. And that's going to give you the mean of your data. Okay? What else he want? the sample standard deviation. Try to create here a bar, call it standard deviation, and do it based on the equation. Then I will show you an easier way to do it, but do it now according to the equation. Standard deviation is the square root of what? Standard deviation, square root, xi minus mu squared divided by n. Just type in STDEV, so standard deviation. Because it's going to be too complicated for you, that equation. It's doable. After you open parentheses, go and select the data that you're interested to see the standard deviation for them, which is from here to here. Hit enter. You're going to find that my standard deviation is 8.37. So type in variance in a new bar equal variance for a sample here. Okay? So you guys realize that Excel is not as weak as you thought, huh? He can do many good stuff for us.